Alright, here we have numbers 8 through 10 for the energy review. And number 8 says, when figuring out conservation of energy equation, or figuring out an equation, you should ask yourself 3 questions. List them. Alright, is it moving? Is it above the ground? And last but not least, is it on a spring? Alright, so these 3 questions are going to help you figure out which conservation of energy equation you have, and it will allow you to solve for whatever it's asking for. Alright, number 9 says, energy is blank work. Energy is the ability to create forces. Energy is stored work. Alright, here we go. An 8, and this is kilograms, 8 kilogram ball is dropped from a 20-meter tall ledge. How fast is it going when it is still 6 meters above the ground? Alright, what kind of energy do you have before? Before, is it moving? No. Is it above the ground? Yes. Is it on a spring? No. So we have potential energy. Alright, just to back up to number 8, is it moving? That's kinetic energy. Is it above the ground? That's potential energy. And is it on a spring? That is potential elastic energy. Alright. So at the end, well, at R here, it is moving. We can see that. So it has kinetic. But wait, it's also above the ground. Make sure before you move on with the equation, ask yourself all 3 questions. Is it moving? Yes. Is it above the ground? Yes. So we have kinetic energy and potential energy. And is it on a spring? No. Alright, so was it that work was done between here and here, or was the energy just being transferred? Well, we know the same amount of energy here is the total amount of energy we have here. So it's not that we were doing work to the system, we just are transferring our energy, so no work. So our conservation of energy equation is going to look like this. The energy we had before, which is potential energy, equals, since we don't have any work, we wouldn't do plus or minus work, the kinetic energy and potential energy that we have afterwards. Alright, to solve for how fast it is going at R, so we want to know afterwards. So on this side of the equation, how fast is it going? So we're going to plug in all of our equations. So potential energy is mgh, and then on the other side we have kinetic energy, which is 1/2 mv squared plus mgh. Now, some of you might be thinking, we have an mgh on one side and an mgh on the other, why can't we just cancel them out? Well, first of all, we have an mgh which includes a height before. Well, our height before is 20 meters. On the right side, we have energy afterwards. Our height afterwards is only 6. So these are actually entirely different numbers, so we can't do anything about them. Alright, so we plug in our numbers. Our mass is 8. Gravity is 10. And our initial height before is 20. Afterwards, we have 1/2 of our mass, which is still 8, times v squared, which the velocity is what we're trying to solve for, plus mass, which is 8, times gravity, which is 10, times our new height, which is 6. So we multiply 8 and 10 and 20. On the left side, 8 times 10 times 20 is equal to 1,600. So 1,600 joules of potential energy equals, and the total of these will equal 1,600 joules. But we're trying to solve for velocity here. Well, 1/2 of 8 You guys see that right here. 1/2 of 8 is 4, and then we have v squared plus 8 times 10 times 6 this time. So 8 times 10 times 6 is equal to 480. So our next step is to subtract 480 from both sides. So on the right side it goes away, on the left side we do 1600 minus 480. And we get 1120. So 1120 equals 4v squared. So what we can do next is divide both sides by 4. This cancels out. And 1120 divided by 4 is 280. So we end up with 280 equals velocity squared. Are we done? Nope, we have to take the square root of both of these in order to get our velocity. So the square root of 280 is equal to 16.7. So our velocity here is 16.7 meters per second. Okay. If it then crushes the box to stop at the bottom, how much work is done on the box? Well, the work that has to be done to the box would be equal to the kinetic energy that it had right before it hit the box. Because if work is being done and then the object stops, work is how we add or subtract energy from a system. So if the object stops, all that kinetic energy goes into that work. Well, the kinetic energy at the bottom is equal to the potential energy at the top. So we know potential energy at the top is equal to the kinetic energy at the bottom, which is equal to the work that we would have to do to take all that kinetic energy away. So all we have to do is mass times gravity times height. So at the top, it's mass is 8, gravity is 10, height is 20, and we actually figured that up, 8 times 10 times 20 on this left side. Remember our potential energy before, and it equals 1600 joules. So that's how much work was done. Alright. If efficiency is less than 100%, it is usually due to what? Well, it's usually due to what we call negative work or friction.